So I'd like to thank the organizers, in particular Shayan and Nikhil, for having me here. So I'll be talking about some polynomials that I think that are actually very similar to the ones that Ryan O'Donnell mentioned in his talk. But these polynomials will be related to general matrices, not necessarily adjacency matrices of graphs. So the setup was this thing. So if you recall, this is actually a corollary of the main theorem that Marcus Spearman Srivastava proved. So this was known as Weaver's conjecture. The result was the following. So if you have a collection of vectors in Cn whose square norms are less than or equal to half and which are isotropic in this sense, then you can partition them into R blocks, so that when you restrict to each block, the maximum eigenvalue can be bounded by this quantity, which is which turns out to be strictly less than 1 for, in this case, for R bigger than or equal to 12. And this resolved the so-called paving conjecture of Anderson, and which in turn resolved the Cadison-Singer problem. So this is the paving conjecture. So suppose you have a matrix A. The goal is to find a block partition of the matrix using diagonal projections with the following property. So the conjecture was that for any zero diagonal contraction, then you can find, by contraction I mean the spectral norm is less than or equal to 1. So the conjecture was that for any such zero diagonal contraction and for any epsilon less than 1, there is a R which is universal, that doesn't depend upon the matrix or the dimension, so that when you cut down this matrix using these diagonal blocks, the norm is less than epsilon. And the point was that if you can show this to be true for any epsilon and any R, since this constants epsilon and R are independent of the dimension, then this translates to an infinite dimensional statement, and which was equivalent to the Cadison-Singer problem. Now Marcus Spearman Srivastava, the result in the previous page, it translates to the following in this setting. So now you let the matrix be Hermitian rather than general. You preserve this condition, the zero diagonal condition. Then you can find these projections with this required property, but with a maximal eigenvalue in terms of in place of the spectral norm. And they also gave a quantitative estimate. The number of blocks needed scales as 1 divided by epsilon square. So as I mentioned, this resolved the Cadison-Singer problem. And the remarkable thing is that, if you want the norms of these matrices to shrink, if you took the identity matrix, that won't work. So some condition was needed. And the remarkable thing is that the only thing that you need is that the diagonal be 0. Now, there are easy examples that show that even in this theorem, if you look at how R scales with epsilon, you cannot expect to do better than 1 divided by epsilon square. And the estimate in the previous page, and also, but if you want some quantitative estimates, not an asymptotic result, then the previous result says that you can take the number of blocks to be 12. Again, for this last statement, must be mentioned that again, there are simple examples that show that you cannot take R to be equal to 2. 2 blocks are not enough. It is conceivable that 3 is enough, but we haven't been able to prove it yet. I'll mention a slightly stronger result later on in the talk. Now, if you recall the distinction between these two theorems, first of all, you let the matrix be Hermitian and you only control the largest eigenvalue. Now, if you wanted to pass from this to that, so I would call this one-sided paving of Hermitian matrices. I would call this norm paving of general matrices. Now, using simple linear algebra, what you can see is that, I mean, you do this 4 times. You do this construction 4 times. So, both for the real and imaginary parts of the given matrix. And if you put that together, you get the following result. That Anderson's original conjecture is true, but with the number of blocks, now you have to take a product of paving. So 1 divided by epsilon square, you have to multiply it with itself 4 times, and you get 1 divided by epsilon to the power of 8. But as I said, this is enough for the Cadison-Singer problem. But it was, well, at least I was curious, can this be improved? Now, what kind of improvement could we expect? So there is this, before the resolution of the Cadison-Singer problem 25 years ago, Burgan and Zafriri showed that if instead of wanting a partition, you just wanted one large block. So they showed that you can get a block of size n times epsilon square. So I mean, morally this would suggest that that n divided by n epsilon square, O of 1 by epsilon square blocks might be enough for the Cadison-Singer problem. And there is a simple example over here that says that that says that you need at least so the scaling of this is the example that I mentioned. So there is a simple linear algebraic example that I don't want to spend much time on that says that that O of 1 by epsilon square blocks are needed. So now this thing that remember that if you wanted to go from one-sided paving to norm paving, we had to do we had to solve 4 paving problems in parallel. Now more generally we could ask suppose we have a collection of matrices. Let's see, in this case we have 3 different matrices. You want to find one block partition that works for all the matrices simultaneously. Now here there's another question that you could ask. Suppose you have k matrices, then how does this what is the dependence on k for the number of partitions that you need? Now once again this is a simple example. There is a again a simple example, a homework problem that that says that if you have k blocks, the MSS proof gives 1 divided by epsilon to the power of 2k. And you can play around with it. So at least that for a single matrix you need more than or equal to 1 by epsilon square blocks. And I think I should mention that if you have k matrices, one can show that the number of blocks should scale linearly with the number of matrices. So if you wanted to get this kind of multi-paving result, from the paving result for a single matrix, I mean, let's see, what this, can you tweak the main MSS theorem to get this result? So there was this one generalization that was apparently proved independently by several people that says the following thing. So in the original MSS result, so these matrices AI were restricted to be rank 1, but then it was observed by several authors that that condition can be dropped. And this is something that Nikhil had mentioned in his bootcamp talk. You get exactly the same estimate, but now you need this condition, that if these are higher rank, then again, the control that you get is in terms of the trace. And, this is not very satisfying. And there is some reason to believe that, instead of these trace, you should be able to control it by, by the log rank or some such thing, but that currently is still open. And the problem is that if you try to apply this to the multi-paving result, if you took sums of matrices, then that is too weak, for what we want. So you would want to prove this kind of result, that if you have k different collections of vectors satisfying this condition, again you would want to find a common partition that achieves the MSS bound. So this is something that that we were able to prove together with Nikhil. So the lower bound is the following. So you can easily construct these k matrices, again with this condition, so that the number of blocks that you need scales as 1 by epsilon square with regard to epsilon, and linearly with regard to the number of matrices. And again, this is an easy thing. And a little while ago, we were able to show that, together with Nikhil, was able to show that actually you can get a result that matches the lower bound, both with regard to k as well as epsilon square. And this will involve tweaking the method of interlacing polynomials in a fairly natural way, which I will get to. Now, to do this, in hindsight, this is the most obvious thing that we could have done. So, starting with a matrix which is Hermitian, you take any partition of the index set and you write down the corresponding paving. So these PIs are now diagonal projections, and you look at the sum of these. So this is a diagonal block matrix. Then the method of interlacing polynomials would immediately tell us, try to see if there is some kind of interlacing going on here. So what you do is, for every paving, you look at the characteristic polynomial of this block compression and you add it up. So you look at the expected characteristic polynomial. First of all, is it real rooted? It turns out that yes, it is real rooted. And the next thing one would have to prove is that, can you control with non-zero probability the largest eigenvalue of one paving using the expected characteristic polynomial? And that again, can be done. And for people who have ever worked with interlacing polynomials, actually these facts should be fairly routine to prove. And then the main part becomes how do you control the largest root of this expected characteristic polynomial. In this case, the expected characteristic polynomial has a very simple expression. So what it just turns out to be, you take a determinantal polynomial. So here this z, the z is a diagonal matrix of indeterminates. So it's a diagonal n by n matrix with z1, z2, zn on the diagonal. You raise it to the power of r. You're looking for r pavings, and then you take a suitable iterated partial derivative. And then after you take all these, this becomes multi-affine, and then you specialize. You set all the diagonal variables to be equal to each other, and that is exactly what this, by the way, this should be r. This is exactly what this expected characteristic polynomial is. And then it becomes, how do you bound the maximum root of this? And this is typically done using some kind of barrier argument. So there are two ways of doing it. One, maybe you could find a combinatorial interpretation of this. Now I should remark that this polynomial that you have over here, this is actually exactly the polynomial that Ryan O'Donnell mentioned in his talk. So you can write this in another way. So suppose you have actually the matrices don't have to be the same. So suppose you had a collection of matrices. So what you could do is, you could look at, so these are all matrices and these are all Hermitian matrices. So what you could do is, you could look at the characteristic polynomial of A1, now these DIs, so these are diagonal matrices of plus ones and minus ones, and then you look at the expected characteristic polynomial over, so these are diagonal plus minus one matrices, and then you take the uniform distribution on all these matrices, and then you average the characteristic polynomial, which, if you might recall, is exactly the expression that Ryan O'Donnell had in his talk. So you would like to prove an upper bound. So in his case, he was the matrices that he worked with had additional structure, and he was able to use combinatorial arguments to get a grasp on what the largest root was. But here we will actually have to make some calculations. And so these kinds of things, again, these things you typically use these barrier type arguments that were also introduced by Marcus Speelman Srivastava. So now one thing initially, that when you write down this polynomial, I should mention that this polynomial that you have over here, you can also write it out purely as a univariate polynomial. So what you do is, so if you look at the, so this is just the expression of for the determinant, but lacking this term, this r to the power of number of cycles. Where sigma is, if you take a permutation sigma, you look at the number of cycles, C of sigma, and then you just tweak the determinant by adding this term. So let me call this the R determinant. Similarly, you can write down the R characteristic polynomial using the R determinant. Then it turns out that actually this expected characteristic polynomial is precisely this. I mean, this looks like a fairly concrete object, and spend some time trying to use this expression to prove root bounds, but unfortunately, we couldn't get it to work. And actually, it's not at all obvious, by just looking at this expression, that this R characteristic polynomial has this following property, that whenever you evaluate it at a Hermitian matrix, the polynomial is real rooted. I mean, this is not at all apparent, when you first look at it. And however, by the way, this real rootedness doesn't work for R, which is not a positive integer. This thing has been studied, not the polynomial as such, but this expression, this so-called R determinant, has been studied in the past. This has shown up quite independently of each other in half a dozen places. So there is a different normalization that is called the alpha permanent, and so on and so forth. And the one thing that we do know about this R determinant is that whenever you evaluate the R determinant at a PSD matrix, then it is positive. And the only values of R, so that for every PSD matrix it is positive, are exactly those when R is a integer, positive or negative. Now, this thing that I mentioned about this expected characteristic polynomial, so here what we are doing is that we are summing over all pavings, and we could think of it as putting a uniform distribution over all pavings. But the entire thing also works in a slightly more general setting. So in the setting of strongly Rayleigh measures, so recall that a measure on subsets of n is called a strongly Rayleigh measure if this generating polynomial is real stable. So these were introduced by Borsia, Brandon, and Liggett in 2008, 2009. And it turns out that instead of just averaging over all partitions uniformly, if you average them with respect to any strongly Rayleigh distribution, then the same thing works. And this can be read off from a result that Mimar mentioned earlier this morning, that you do exactly the same thing. So you look at the expected characteristic polynomial, but with regard to a strongly Rayleigh distribution, then the whole thing works. The method of interlacing polynomial works. This expected characteristic polynomial is real rooted, and actually one can write down what the expected characteristic polynomial is. So root bounds are typically proved using this barrier method. So you look at the log barrier. So it is known that if you have a real stable polynomial, then you define this thing, this generalization of the points that are, for a univariate polynomial, the points that are bigger than the max root of the univariate polynomial. So you say that that a point A is above the roots if it does not vanish on the positive orthant based at A. Then it's a classical fact that this thing, the set of all points above in the univariate case is an interval, it's a half interval. I'm sorry, it's a half infinite interval. But in the real stable case, in the multivariate case, it is known that this set is convex. And further, that this set, when you take the derivative, this set above the roots, it can only become larger. And the whole point of the barrier method was to get a estimate on how, by what factor, to what extent this set above the roots increases in size when you apply a partial derivative. So this is done using this log barrier, which is just the log of the real stable polynomial. And this thing, the log barrier, it has several nice properties. It is positive, it is decreasing along each, when you take the partial derivative, then it is decreasing, and then it is also convex. So using this, and in a way that is, so what you would like to do is, you would like to get an estimate on the set of all points that are above the roots of this polynomial, and sort of you run the machinery, and what one gets is the following statement. So this it just involves making a careful calculation that we did together with Jonathan Leake. So it says the following thing. So the pictorially this is what it says. So let me do the setting when the real stable polynomial is of let's say at most is of degree 2 in each of the variables. Then you are going to have a set which is above the roots, and suppose you have a point that is above the roots of this polynomial. Then what you do is you look at the univariate restriction in any coordinate direction. Then what one does is when you take the derivative, these things move to the left, but by what extent? So this theorem would say in the case when r is equal to 2, you can move halfway to where the largest root of this restriction is, which again if you make some manipulations, you get an expression of this kind, but now involving the smallest root. So this would be in this setting. This would be lambda 1 and this would be lambda 2. So to get refined estimates, one would actually have to say that now you're sort of turning it on its head. What can you say about the smallest root of a univariate restriction? For the special polynomials that we have, polynomials of this form, determinant of z minus a, powers of determinant of z minus a, as well as partial derivatives of such polynomials, then one can get an estimate in terms of the diagonal entries of the matrix that we started off with. And if you put it all together, you get the following theorem, which was proved jointly with Jonathan over here, that the largest root of the R characteristic polynomial or the expected characteristic polynomial can be bounded by this quantity. And in particular, that this result would say that when you have a zero diagonal Hermitian contraction, then the largest root is strictly less than 1 by universal quantity when r is equal to 4, improving the MSS result of 12. Now, there is one thing, that this thing actually fits into a slightly larger context. MSS had introduced, this notion of the additive convolution of two polynomials. So if you have two real rooted polynomials of degree d, let's say monic, you write them as characteristic polynomials of matrices, and you define the following operation. So you look at the expectation over the unitary group of the characteristic polynomial of A plus a random rotation of P. Now, because of the fact that we're taking random rotation, so this is an expression that only depends upon the eigenvalues of A and B or the roots of P and Q, and it's a lovely fact that that this additive convolution is real rooted. Further, it is very simple, by just this thing that you have an estimate, for the largest root of P convolution Q, but indeed you can prove something stronger. And this was key to their paper on that MSS4 on Ramanujan graphs. So it says that, and this is they proved a version of this when R was a polynomial of the form x minus alpha times x to the power of n minus 1, and this generalization was noted by Leake and Ryder. So this is something that they refer to as a submodularity property, and this is tight, and this cannot be improved. And this result, if you iterate this R times, so you get the following thing, which again, so this is that Ramanujan bound showing up. Now, now the thing is, for these optimal estimates, the Cadison-Singer problem, one would like to hope that, some similar result holds in the multivariate setting. There is a natural candidate for a multivariate additive convolution, which is just this. So, more generally, this, for any if you have two multi-affine polynomials P and Q, in this case they are determinantal, but it doesn't matter. You could write down this expression. You take the partial of P with respect to a subset and multiply by the partial of Q with respect to the complementary subset, and you add it up. This operation preserves real stability. If you start off, if P and Q are real stable to begin with, then this polynomial will also be real stable. And everything that we would want to prove would follow if this kind of submodularity, which I mentioned in the previous slide, this one, if this kind of submodularity were true in this setting as well. And but unfortunately, that thing is not true, and I don't think we really understand why this is not true. And understanding why this is not true and whether this can be fixed, would be a really nice exercise. So then one can prove something weaker, which can actually be read out, from the estimate that I had given a few slides previously. But that we would like to remove this. We would just like to keep this term, but that doesn't seem to be true. Now, all of this thing, that another way of approaching this, would be by looking at this, this fundamental operation, that it is known that when you start off with a real stable polynomial and you remove all terms that contain powers of variables, so you project it down to the multi-affine part, that preserves real stability. This is a result of Bocia and Brandon. And one can write down all the polynomials that we looked at over the previous slides using this multi-affine part operator. And so really, everything boils down to, once we start off with a real stable polynomial about which we know what the roots look like, then can you get tight estimates for the, in this case, the hyperbolicity cone of the multi-affine part of P. And the point I would like to make is that that the natural conjecture that one could come up with is not true. It's not clear what the correct analog should be. Now this thing, what one can do is one can prove some weak results. So for instance, if you have two real stable polynomials and you apply the second real stable polynomial as a differential operator onto the first, then the one consequence of this theorem of Lieb-Sokal would be that this polynomial is also real stable. So one can use these log barrier techniques to get a handle on the location of the roots. So using some combinatorics, so one can write down this operator in a slightly different form, and using this one can prove the following result, that using the log barrier techniques, one can get estimates for what points lie above the roots of this convolution. But unfortunately, once again, this only gives you that the estimates up to a O of 1 factor, and one can sort of tweak this and make it more general, but what you get is unlikely to be tight. But going back to multi-paving, so we have a handle on how to prove estimates for the largest root of the R characteristic polynomial and so on and so forth. So this, all that works for a single matrix, but what if you have a collection of matrices? Now here, if you'd like to make the method of interlacing polynomials work, so you want one paving to work for all of them. So what one would do is one could take the characteristic polynomial of this, you fix a paving and you multiply the characteristic polynomials, but then in that case the method of interlacing polynomials does not work, because the key thing is that in all applications somehow the polynomials that you work with have to be written as specializations of suitable multi-affine polynomials. So here, we introduced this thing together with Nikhil. So there is this object called the mixed determinant, which again has shown up now and there. What the mixed determinant is, if you have a collection of matrices, you look at so you take a partition of the base set and you multiply the restrictions, the block restrictions of these different matrices relative to these elements in the partition. So this object is called the mixed determinant, and it has, if all the AIs are positive semi-definite, that this is also then this is positive, and so on and so forth. And again, you cook up a univariate polynomial using this. This normalization factor is to ensure that when all the matrices are the same, then what you get is exactly the R characteristic polynomial. And with this in hand, the entire interlacing machinery works. But before that, you would actually like to say that that this single polynomial that you have written down, that when you have a tuple of matrices, you write down the single polynomial, that somehow you can use it to control the eigenvalues of the max eigenvalues of all the matrices in the tuple, and it turns out that that is indeed the case. By a fairly straightforward convexity argument, one can show that this single polynomial controls the max root of all these k polynomials up to a factor of k, which is asymptotically tied. You can't do better than that. And with this in hand, once you can make the method of interlacing polynomials work for this polynomial, you can relate it back to the individual matrices. So now you have this root bound, that I had mentioned that for a single when this thing one of the the estimates that the MS has proved can be used to show that for a single matrix the R characteristic polynomial max root of the order 1 by root R, but then it also works for a tuple of matrices. So when you have a Hermitian tuple where every matrix is a zero diagonal contraction, then you have an estimate on the largest root of this mixed determinantal polynomial, and the factor that you get is of the order O of 1 by root k. And this thing, so this is how we make the method of interlacing polynomials work. So given a partition and a tuple, so you write down this associated polynomial, and for these collections of polynomials you can use interlacing arguments. So you can relate the mixed determinant polynomial restricted to one partition using the expected characteristic polynomial, and now there are each A has k matrices. You take this tuple R times, so you have a total of R times k matrices, and so this is the estimate that one gets. And putting it all together, one gets the following theorem, that when you have a collection of zero diagonal Hermitians, then there exists a common paving, a paving that works for all of them with the right asymptotic dependence. Now this thing, there was some interest in this problem. So if you specialize this to a single, if you go back to Anderson's original conjecture, that says that yes, indeed, you do get the right asymptotic dependence. There was some interest in this problem because of this question that Johnson, Ozawa, and Shechtman had looked at. It's a very basic question in linear algebra. It says the following thing, that if you have a zero trace matrix, we can write it as a commutator. But then you would like to find a commutator decomposition whose norm is as small as possible. And it is, I think that that one should be able to do it with a constant that does not depend on the dimension n, a dimension independent constant, but using this thing. So they had used a weaker version of the result that I mentioned to show this, that this constant can be taken as growing slower than any polynomial in n, but then using our theorem we were able to improve it to something sub-exponential. Now there are a couple of so this thing, I think I'm going to end early. There are a couple of things, a couple of curious questions that I'd like to pose and solicit any insights that you might have. So recall that this was the definition of this R-determinant. So this thing, there are some hardness results about the R-determinant that are known. So in terms of the Tut polynomial, so Mertens and Moore showed that when this is for R that is an integer. So this thing that calculating the R-determinant is hard because you can relate it to evaluating the Tut polynomials of certain associated planar graphs, for which a lot is known. So it is known that the Tut polynomial / be hard to evaluate even for planar graphs unless the parameters x and y lie in a very, very specific domain. And further, approximation schemes, it is known that it's also hard to approximate in certain regimes. But the point is just because this quantity is hard to evaluate, it does not necessarily mean that that the max root of the associated polynomial is hard to approximate or evaluate or some such thing. So there are these curious things that numerical simulations seem to show up, that this polynomial seems to become very well behaved. I mentioned that for R that is a positive integer, this is always real rooted for any Hermitian. But if R is sufficiently large, whether or not it is an integer, somehow this polynomial always seems to be real rooted. And another very curious question, that came up is the following thing. So here, this quantity that we have over here, so this is a class function of the symmetric group. Now, for any class function of the symmetric group, one could write down this expression and write down the associated polynomial. And something I've been wondering about, for quite some time now. What are the class functions that have the following property? That this polynomial is real rooted for every Hermitian, and I think that these are the only ones. But this is something that I've not been able to prove. It's a basic and fundamental question, and I'd be really curious to know the answer to. So we'll end here. Thank you.
But